Okay, welcome back, everyone. Hope you had a good long weekend. So we're going to continue where we left off with the multivariable linear model. And so in this case, what we have is, maybe let's back up a moment. So we have the data comes in the form of pairs, where you have a label or a target, and then you have a corresponding vector. In this case, it's a row vector of the different things you will use to predict that target. And so we always have n samples on our data set. So we have n of these rows in the X matrix that contains the features, and n rows in this Y column vector that contains the targets. And in the multivariable linear model, we say that our modeling choice is that the target is approximately equal to some offset or intercept beta 0 that we can choose times some weighted versions of all of our different features, and we can choose all of these different beta coefficients. And we give a name to this. This is y hat, which is our prediction of this y. And so here we're not using any I indices. We use I indices whenever we want to talk about the ith feature in our data set. Here, there's no I indices. This is sort of a general expression that could hold for some unseen features that are not part of the training data that we see out in the wild later when we're applying this. And if our model is good, then there won't be too much of a difference between our prediction y hat and the truth y. Or in other words, the prediction error epsilon will be small. So our job is to design these prediction coefficients, the betas, that make this error as small as possible. And there's different ways of defining small, but what we said is that we're going to look at the sum of squared errors. We're going to try to minimize that. And now you see the indices y that correspond to the training data. So each of these targets is a training target. This is the prediction of that ith training target. This is the error on the ith target, and we're summing over all samples I in our training data set. And this is what we call the residual sum of squares, or RSS. So here again is our model. Or actually, it's our prediction. So our model maybe technically would be like saying this is approximately equal to yi, but this is the prediction. And here you see the I indices because we're looking at the ith sample of the training data. And we have a visualization of this here. This is in the case where we have two features and only two of these features. In that case, we're plotting the value of one feature on this axis, the value of the other feature on this axis, and the value of the target on this axis. You can see all of our data points, which are these black dots, and then you can see the prediction model, which can define a prediction y hat for every possible value of x1 and x2. You can look up that value and you can find this is the corresponding prediction. And then if you look at the difference between that prediction and the actual data, those are these red lines, and they show you these epsilons. They show you the error. And what we said is that we have, we can look at the slope of this rising line here. That would be beta 1. The slope of this line would be beta 2. And if you looked at the intercept, which is when the x values are both 0, that would be controlled by beta 0. So beta 0 raises and lowers this entire plane. Beta 1 tilts it in this direction, and then beta 2 tilts it in that direction. Okay, so that's that's where we are now. Any questions on anything we've talked about here? Okay, great. We also defined some vectors and matrices, which we'll use. So let me just quickly review that. So it helps to move all of our designable parameters into one vector, which is this beta vector. And as you can see, there's d plus 1 parameters. And in order to express y hat I, the prediction for the ith quantity, we have this equation from before. We can also write that as an inner product between this vector and this vector. But you can see that the beta 0 is multiplying against the 1 because it does not have a corresponding data sample like x. So this is how the intercept is treated. It multiplies by 1. All these other slope coefficients, they multiply their respective x's to get you the y hats. And we can stack the y hats into our prediction vector, the predicted vector of labels, like this. There's n of them. We can stack these as rows of a new matrix, which we're going to call A. And then we have this vector beta. And all together, we can write the equation this way. So our vector of predicted training labels equals this A matrix that contains all our training features times the beta vector that contains our adjustable coefficients. So this is all training stuff. Once we have trained our model and we want to apply it, we can plug in some new features that we use for prediction, and we can get this predictive value y hat, and we may or may not know the true y. In practice, we don't know it, but this is our prediction of what it is. Okay, so here we have the vectors and matrices that we need to move forward. Everybody good with this? Or any questions on this? Okay, great. So we're going to continue with defining our quantities in terms of vectors and matrices. So this is the quantity RSS that we are interested in minimizing. Beta is not shown explicitly on the right, but the beta vector, if you remember, those coefficients control our predictions y hat I. So we'd like to know, is there a more concise way of describing this in terms of vectors rather than summations? And so for that, we can use the norm, or in particular the Euclidean norm of a vector. Let me see. So is Yang Ziqian Guo here? Okay. So how do we write the vector x? How do we write the norm of x in terms of the elements? Let's call them xi of x. Okay. What about Frank Hegedus? All right. What do you think, Frank?
The square root of the sum of the components.
Okay. So it's square root of the sum of the squared components. Yeah. And if you want to visualize this, so here we would have a three-dimensional example where we have x2 is along that axis, x1 is along that axis. Is that right? Yes. And x3 is along that axis. And if we have a point over here and the origin here, and we want to measure the distance, the straight line distance between those 2 points, you can do that in terms of the components. You would take x1, square that. You take x2, which is this distance, square that. And then you take x3 distance, square that, sum them all together, and take the square root. And that's how you get the distance from here to here. Okay, so this is a Euclidean norm. There are other norms like the L1 norm, in which case you don't have the square root and you don't have a square. You instead have absolute values. We'll talk about that a little bit later, but for now we'll focus on this Euclidean norm. And this is just one measure of distance or length. Okay, so now that we have the expression for the norm and the expression for RSS. How can we write the RSS using a norm? So let me ask Charles Irons. Charles here? No. What about Terrell Redding? No. What about Eric Wang? Okay. So how can we write RSS in terms of this norm?
Y minus the norm of x. I don't know.
Okay, so basically the key thing is that, let me write it over here. So we can write x quantity squared, can square both sides of this, right? If I square both sides of it, I get rid of the square root on the right. Okay, so now this expression looks a lot more like this one. The only thing we have to do is instead of using xi here, we have to use yi minus y hat I. And correspondingly, instead of using x here, we have to use y minus y hat. So putting those ideas together, we get the norm of y minus y hat, like this. Is everybody okay with that? Okay, or we could go one step further and we could plug in the expression we have for y hat that involved a and b. Let me ask, is Hannah Wang here? Okay. What about Alan Abdulnoor? Okay. What do you think, Alan? You just got to remember the expression for y hat. You saw it earlier today.
Isn't it all the b?
It's just the matrix A times matrix beta.
That's right. Matrix A times matrix beta. Okay, so now basically what we've done is we have this thing we want to minimize, RSS. We have expressed it as a squared norm of all the key quantities. We have a vector of our training targets. We have a matrix containing all of our training features, as well as an additional column of ones. And we have the designable parameters beta isolated in a vector. And now we can start to move forward and see how can I choose the beta vector to minimize RSS. Okay, so this is a pretty common way to express RSS with this squared Euclidean norm. Okay, any questions? Everybody good with this? Okay, good. So let's take a moment to reflect what we've done or kind of the approach we're taking. And basically what we're doing now is what you do for any machine learning problem. This is just the first time we're doing it. We're going to do this many times before the semester is over. So to solve a general machine learning problem, you assume some model with some tunable parameters. In our case right now, we're doing this linear model, the parameters of these betas. Then you get some training data. In our case, we assume we have training data, which is pairs of vectors x and scalars yi, and we have n of such pairs. We want to choose a loss function, something that measures how well beta is performing on that training data. And in our case right now, we're choosing the residual sum of squares. And finally, the last step, the thing we need to still do, is find the beta that minimize that training loss. Okay. So that's what we're going to do for all the different machine learning problems. But in some cases, the model will be different, the loss function will be different, the parameters might have a different form, and so on. Okay, any questions on big picture? Okay, great. So let's go on to minimizing RSS. So what I've done here is I've plotted what this looks like, this cost or loss. This is a very simple example just so we can visualize it. This would be the case of d equals 1. We have a single feature, and so we have two parameters to adjust, which is the slope coefficient on that feature and the intercept, that constant shift, beta 0. And so here we have the RSS, the vertical axis. And you can see that, remember, we want to minimize RSS. You can see that there's some combination of beta 0 and beta 1, which would be right at the bottom of that curve, right? Right at the bottom of this, like, this bowl. That's what we want to find. We want to find those values of beta 0 and beta 1. So does anybody see something just from this picture that's kind of special about the bottom of the bowl in terms of the slope? In terms of the slopes?
Maybe 0.
Yeah. When you're sitting at the bottom, any direction you look in, the slope is 0, meaning it's not going up or down. It's no matter where you look. And in this two-dimensional case, it really suffices to just look in the beta 0 direction and the beta 1 direction. And we want to find the place where the slope is 0 in those two directions. And that's all we want to do. And it turns out that there's a nice mathematical construct for doing this called the gradient. The gradient is just a vector of the partial derivatives of this loss with respect to each of the individual coefficients. So in general, we have coefficient beta 0 all the way through beta d. And so we have here the gradient of the loss with respect to each of them, and we just stack them all. And at the optimal least squares beta, this entire vector will be equal to all zeros, or in other words, the 0 vector. So that's our technique right now to solving this problem. Here is another visualization using something called a quiver plot. So basically, the arrow shows you the direction and the magnitude of the gradient at any point. So this is like at the point where beta 0 is 2 and beta 1 is 3 is here. You can see the gradient or the slope is, it's like the vector slope at this point is rising uphill in that direction. So basically the gradient tells you the steepest direction uphill as well as how steep it is. So the longer this little arrow, the steeper it is there. And you can see as you get towards the center, the arrows shrink. And when you're at the very center, the optimum point, the arrows have 0 length. So if I go over here, this is the direction uphill. If I go over here, this is the direction uphill. If I go over here, this is the direction uphill, and so on. So that's another way to visualize the gradient. We will be talking a lot more about the gradient in Unit 6 when we talk in detail about optimization. There's some mathematical theory that says if the loss function is convex and differentiable, then this approach, which is finding the 0 gradient point, is basically necessary and sufficient. So that's our approach. We're not going to get into all the math of this at this point. Just kind of take it on faith that this is what we need. And so here we see basically the kind of main idea is that these are the parameters we're looking for. These are the least squares values of the betas, and they are the ones that make this gradient equal to the 0 vector. So this boldface 0 is a vector of column vector of stacked zeros. Okay, so that's the idea. Any questions? All right, have you guys seen something like this before? I'm just curious, in another class? Okay, I see some yeses and some nos. Okay, so now we gotta, basically the next step is to is to derive the expressions for these partial derivatives, and then from there we'll figure out what is this least squares beta. So we've looked at this RSS expression before. We expressed it as a squared norm and so on here. When we do calculus in this class, because there is such thing as vector calculus, where you can take derivatives with respect to vectors and matrices and so on, but I'm assuming you guys don't know that. So whenever we do calculus, we're going to go back to the world of scalars and summations, do our calculus there on scalars, and then map back to the world of vectors and matrices. Okay? So in other words, we're not going to try to take the derivative of this with respect to the beta vector, because I don't think most of you have seen that yet. So instead, we're going to rewrite that expression using a sum. And now we're going to use another sum to write this. Does anybody remember? Actually, let me ask, is Zhujun Bai here? Zhujun Bai? No. What about Sam? Sam Benger. How do you pronounce it? Benjigurtis. Yeah, do you remember how we can write this guy as a summation?
Wasn't that just A times beta?
Okay, so this is a scalar. This is the ith quantity in the vector you're thinking of. So we had this vector y hat. Now we're looking at the ith quantity. It's like the prediction of the ith training target. We want to write that in terms of the ith training features and the betas. And it's going to be a sum. And let's use the summing variable j. We always have d features, so I'm going to write the sum from 1 to d. Actually, we're going to cheat a little bit. We're going to start this at 0 because we do have a 0 coefficient for beta. So do you remember, Sam, what we put in here?
That's like the beta 1 times
So yeah.
0 plus beta 1 x 1.
Okay. So we have to involve all the betas. So since I have a sum over j terms, I'm going to invoke all the different beta j's here. And then I need one more thing to multiply. So the jth beta multiplies by something very particular. It has to do with that A matrix. Remember that?
Xi.
Okay, so yeah, so it's an xi except for the beta 0 term. That doesn't have any xi to multiply. And so we created this new matrix A that added that extra thing. So that new matrix A is going to have Aij, that term. And that includes the one that the beta 0 can multiply against. Okay, so this is what we have. So we have this kind of messy expression. It has two summations. But this is really the one that tells us how RSS depends on the individual beta j's. And this is the thing we're going to use to do calculus. Okay, and now we're going to start doing calculus. And calculus, it's basically like machine learning is linear algebra and calculus. Those two things mixed together. And so here's the first time we're involving the calculus component. So what we want to do is we want to look at each of these terms. There's basically two flavors. There's the one with respect to the beta 0 has one form, and then the one with respect to the slope terms has a different form. So let's first, in this case, because we're using the A matrix, they all have the same forms. So what we can do is we can just look generically at the jth beta coefficient and say, what's the partial derivative of this with respect to beta j? Okay, so the way we always tackle this is we apply the chain rule. Because you can see the beta j is kind of nestled within this quadratic and within this sum and that sum and so on. So the chain rule will be our friend. We're going to be doing a lot of chain rule stuff. So the way to think about the chain rule is that this derivative operator is linear. And by linear, I mean that if you take the derivative of the sum of two things, that's the same thing as the sum of the individual derivatives. Or if you take the derivative of a scaled thing, that's the same as the scaled derivative of that original thing. So that allows us to move this derivative through the sum. So we kind of just move the derivative through the sum. We put the sum here, and then we say, okay, now let's figure out the derivative of that. So here's where we have to use the chain rule because we have the square. So if you remember your chain rule with the square, the derivative of this is going to be 2 times this entire thing times the derivative of this with respect to beta j. Okay, so we have to be a little careful now. Over here, we have used j to mean the particular term, the particular beta we're taking the derivative with respect to. If we're not careful, we might use j again, as we did here. We might like plug in the expression with j. And now there's kind of a clash because j is actually used to mean a particular term as well as a variable dummy entry. And if you make that mistake, you can run into a lot of trouble. So what we've done is we've said, let's instead of calling this sum in here, the summing term j, we're going to call it j prime. Just anything that's different from j and different from, like the variable I that's also used elsewhere. So here we have a j prime, here we have a j prime. And now you can see, okay, so what I'm working on here is I'm working on the partial derivative of this. Since this yi doesn't depend on beta j, we don't have to worry about it. So really we have to look at the partial derivative of, I guess, of this thing here. And in doing that, we're going to write that using a j prime to keep it separate from this j. And now, does anybody see, or let me ask, is Luke Carter? Sorry, is Carson Bryce here? Yeah. So Carson, do you see how what would be the partial derivative of this term with respect to beta j?
Probably just the sum of all AIJs. The sum over j prime of AIJ prime.
No. Okay. Let me just write out the beginning part of this. So we're going to have a 2. We took the 2 down. We have the sum in front, and we then have this term times the derivative. So this term alone, I can write that. I'll be a little bit more compact and write this as y hat I down here. And then now I need to write, this is what we're working on, is we're working on what goes there. So in particular, we're looking at this. So remember that this sum here, this sum basically looks like AI0, beta 0 plus AI1, beta 1 plus ... all the way to AI d beta d. And you can see what we're doing here is we're taking the partial derivative with respect to one particular one. Maybe j, let's just say for sake of argument, j is 1. So now knowing that, Carson, do you see what the answer is from this expression? If I take the derivative of that green thing with respect to beta 1,
Well, yeah, you get AI.
yeah, we just get one AI, right? We don't have a sum. We don't have this sum over j prime. Because only one of these terms inside the sum actually depends on beta j. And it's the jth term inside the sum. All the other terms don't depend on beta j, so when I take the derivative, they go away. There's only one term that does, and when I take the derivative here with respect to beta 1, I just get AI1. Is that making sense? Okay, this is like a super important point. This will eventually be obvious to all of you because we're going to be doing it so often, but I just want to make sure that everybody understands this right now because it is kind of just the first little hump to get over. Does everybody have any questions on this? So what I'm saying is this is going to be AIJ. Any questions on this? Oh, there is one little mistake. There should be a negative, exactly, because of this negative here. So I need to put the negative in there, so I'll put the negative there. Okay. If anybody has a question on this, it's good to ask it because other people probably have the same question, so don't be shy. Yes?
So were you saying that the only term that matters is the 1 multiplied by the initial value of j? Or how did you determine it was AI1 specifically?
So I just said, let's suppose j equals 1 for sake of argument. In that case, I get this. That would be the derivative of the sum with respect, right?
So, okay, so the answer is aij, not AI1.
Exactly. The answer is aij.
Okay, I'm sorry. I thought
Yes.
you said that the answer was AI1.
Yeah, only if j is 1. Or like if j is 0, it would be ai 0 or so on. Yes.
So this is for like one particular j. Is j
Exactly.
like the direction we're looking at?
Yes. Yeah, you could say back to this picture, I want to make sure my slope is 0 in these two directions. And so right now I'm just looking at the slope in the jth direction for an arbitrary j, and I have derived that it equals this expression. This is the partial derivative, which is basically the slope in that direction, and that's what it equals. Yes. Any other questions?
So we don't need to add some for that inside about j.
Yeah, we don't involve this sum because if I expand this sum, I get this. And now I can see that if I take the partial derivative with respect to a single beta j, then only one of these terms will matter. All the others will go away. Okay? Good. It seems like you guys are getting it more. Any last questions? Okay, cool. So we have finally this expression. And now we have to do some of that matrix vector gymnastics type stuff. We want to go from this summation expression back to the world of matrices and vectors. And so maybe we can do that down below. So I'll explain how and why we get from here to here. And let's just write the expression we have on the right, except I'll leave out the -2 for now, just to simplify things. So this yi minus yi hat aij, we can begin to think about this. So here we want to express this as like a matrix vector multiply. We have a vector here, and we have a matrix here, and we're summing over the I index. So we want to make sure that the I index is the middle index, and it is. So what we can do is we can say that we have vector y, the ith element, and we have a matrix A, I jth element, and I'm summing over I. Except there's something a little bit strange. If you think about this from a matrix perspective, and let's say we just go forward and say, oh, so what I have is vector y times matrix A. So let me see. Is Luke Carter here? Yeah. So see any issue with this expression? I'll give you a hint. So this is a column vector, and this is a matrix. Is that something we can do? Yeah, so there's a couple things, there's a couple ways to fix it. If we really want to kind of keep this ordering, and this ordering is what kept I as the inner coefficient, we just need to make sure that this is transposed. Because if I transpose that, then everything is fine. So what I can do is I can write y transpose there, and then I have a row vector, and so I just need that this dimension is the same as this dimension, but they are. And then the final thing is realize, oh, actually, I could have put a transpose there because the ith term of y transpose is the same as the ith term of y. Actually, I messed up something apologize, I forgot about the y hat I. So let me, so there should be a y hat term too. I had totally forgotten about this term. Sorry about that. So we have over here, oops. So we have y minus y hat transpose A. Okay. And one other thing is, this is, what I have now is only the jth entry, right? Because here we have a scalar, and so I need to make this into a scalar. It's because I haven't yet put in the fact that I'm just looking at the jth entry. Okay, is everybody okay with this? Yes.
Can you explain one more time why you can add a key without change?
So if I have a column vector and I say, let me be more explicit. If I have like y1, y2, y3, this is column vector y. And I say, what is the second entry? It's just y2, right? If I have a row vector, y1, y2, y3, and I say, what is the second entry? It's y2. It's the same thing. So if I'm asking, if you're asking why can we put the transpose in here, it's because the jth entry of this is the same as the jth entry or ith entry of this. So I'm free to put this in when I'm extracting the ith entry. And in fact, I have to in order to make this a valid multiply. Okay, any other questions? Okay, so for exactly the same reason, we can, this is also a vector, right? This is a vector. And what we're saying is that I'm taking the jth element of a vector. That's the same thing as the jth element of its transpose. So I can transpose this whole thing. And that is exactly how we get to this expression here. So those are the steps to go from here to here. Okay, so some questions on any of these procedures here? Is everybody good? Yes.
Yeah, what do we do for the last step? How are we supposed
To go from here to here?
Yeah.
It's exactly this idea. So what we said is, if I have a column vector and I extract the jth entry, that's equal to the transpose of that column vector extracting the jth entry. So here's a column vector. Actually, this is a row vector. I transpose that row vector, I get the column vector. But since I'm extracting the jth entry, they're equal.
Oh, okay, I see.
Yeah. Okay, great. Okay, so that's how we got to here, basically. And then the last step is I just plugged in the expression, the vector expression for y hat, which is a times beta. And just to kind of step back, what we're saying is now we know that the slope in the jth direction, or the jth component of the gradient vector, has this expression. Okay. So our plan is to find the beta for which we can zero that jth slope for all the different j. So we want this to be 0 for all the different j. Okay, we want this to be 0 for all j, based on the previous page. But that's the same thing as saying that this entire vector is 0. If all of its entries are 0, the entire vector is 0. So that means that A transpose times y minus A beta least squares, that entire vector is 0. And we could also expand out that expression where we would have A transpose Y minus A transpose A beta least squares. And then I could just move this negative term to the left side of the equation, and we get this expression, this equation. And then how do we do that last step? How do we extract beta least squares? So let me ask, is Connor Churin here? Yeah. So do you see how we can solve for beta least squares from here?
I mean, we can just, we can take out, we can cancel the transpose A, and then solve for beta, it's just y over A.
Okay, not quite, because so what we have is we have something of the form. Maybe I'll write it this way. There's some matrix C times our beta vector, and then there's some I'll call it F, some vector F. So this is like a matrix C. This is like a vector F, and this is our beta. And this is a linear system of equations that we want to solve. And so if you remember from here, how do we solve a linear system of equations? Do you remember how we do that? Okay, so we multiply on the left by C inverse on both sides. And C inverse cancels this, so we get the beta, and then on the right, we get C inverse times F. Okay, and this is true if and only if C inverse exists. In other words, the matrix C has to be invertible. It's not always invertible. And one time it's definitely not invertible is if it's not square, if it's tall or wide. And so the problem with trying to, let's say, get rid of A transpose, like sort of invert this, is that A is typically going to be a tall matrix. It's usually not going to be square. So there's no way I can do like multiply on the left by A transpose inverse. It's impossible. But this is definitely going to be square, just by, it's a symmetric matrix. By construction, it's square. And so if it's invertible, we'll talk about that more later, then we can essentially invert this entire matrix, and we get that beta least squares is A transpose A, that quantity inverted, times A transpose Y. Okay. Okay, so usually in machine learning, A transpose is a tall matrix. That means you have more data samples than you do features, or more data samples than you do coefficients you're trying to design. That's the typical case. And in that case, it's not completely guaranteed, but it would be very unusual if this matrix A transpose A is not invertible. Now, there are examples of machine learning where it's kind of strange examples where that matrix could actually be wide. We'll talk more about those in unit 4, I believe. But for now, we'll just assume that that's not the case. Okay, so we finally have an expression for the coefficients, for our least squares coefficients. And you can see it depends on the feature, the training features, and the training labels. Okay, any questions on, yes?
Here, A
inverse, we can now multiply with A transpose to be the identity, right? We have the A inverse in the same.
I didn't hear everything you were saying, but basically this matrix is usually tall. It's not invertible. We can't invert a rectangular matrix. But the matrix A transpose times A, this is a square matrix. And when this is tall, it's very likely that this guy is going to be invertible. So in most cases, this exists, we're good, we can move on. Okay, any questions? Good, so, all right, so basically we have a solution to our problem. This is what we derived. And just to remember, y is a column vector of the different examples of our targets. A is, each one of the rows is a single example of the D features, but it also has this one that is multiplying by the beta 0. And this is correct, this is the least square solution, but just looking at this, it's pretty complicated because of the presence of the ones here kind of getting inside of this product, inside of the inverse. It's kind of a mess. It's really hard to see much insight from this expression. So we're going to kind of back up, and we're going to do a slightly different derivation that's going to give us more insight and more connection with statistics. And so in particular, we're going to separate the roles of the intercept coefficient beta and the slope coefficients. And we're actually going to pack those slope coefficients. Let me show you what we're going to do. We're going to write this y hat as beta 0 plus a new vector that we're going to call beta 1 through d. And this is going to be multiplying our x vector. So we have a transpose here. So this beta 1 through d is going to be beta 1 dot 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 through beta d. So this is a new vector that contains all of our slope coefficients. So what we've done is we've pulled out the intercept because it works in a different way than the slope coefficients. It doesn't actually multiply any data. So that helps to pull it out and treat it differently than the slope coefficients. And with this formulation, we'll do some similar calculus and stuff, and we'll actually get expressions that are insightful that can give us a view of like how this is working and whether it's going to work for a certain data set or not. Okay, any questions on what we have? Yes?
What's the vector x? Is that just kind of like a...
Yeah, x is going to be the vector. That's a good question. Let me put it down here. So x is just going to be the vector of, in this case, the D features that we're using for prediction. So these guys. Okay. All right, so we're going to connect this to sample statistics of the data. So sample statistics are things that you can compute from data directly. They're different from statistical things like mean and variance and so on that are described based on random variables. We're going to get into that stuff in the next unit, but for now we're just going to talk about simple statistics that you can compute from lists of numbers. So we'll start with the very simplest thing, which is the sample mean. And we're going to denote this with a bar on top of the variable. And if I give you a set of yi's, where I goes from 1 to n, remember these are our training targets. If I just take the average of those n training targets, I get what I call y bar, which is called the sample mean. Okay, it's just the average of a list of numbers. We have n numbers, so we sum them up and divide by n. Okay, we can do the same thing with the jth feature. So it's going to be the average. And we're always going to be averaging over our data examples over the variable I. And so here we're going to have xij. So if you remember, I is the sample index in the data set, and j is the feature index. The index of which thing we're using for prediction. So over here, we have the average of the jth feature over our training data. Is everybody good with those? I know you've definitely seen these, probably saw these when you were like 10 or 12 or something. Okay. Sample variance, so that sample mean is like the simplest possible statistic, the simplest way you can summarize a list down to its average. The sample variance is the second simplest thing you can do. You can just say how much does something deviate from its average. And so what you do is you look at yi minus its mean, and you take the average squared value. So you sum over I equals 1 to n, and you divide by n. So it's just the average squared deviation from the samples and their mean. We can do the same thing for the jth feature. So in this case, we average the squared difference between xij and x bar j squared. Okay, is this sort of ringing a bell from classes you've had? Good. So now sometimes students will ask like, okay, I'm using a 1 over n, should I be using a 1 over n minus 1? And the answer is a little complicated. We're gonna postpone a detailed discussion of when you use this one to Unit 3 when we'll talk about unbiased estimates. But for now, we definitely want to use 1 over n and not 1 over n minus 1 because otherwise our expressions will be all wrong. So this is definitely what we want to use for now. And one other term, so this is the sample variance. If you take the square root of that term, you get something called the sample standard deviation. So notice here, we're writing the sample variance as s squared sub y. And so the sample standard deviation is just s sub y. These are just standard terminologies that you find in basic statistics. So we're just adopting those notations. Okay, what about the sample covariance? Let's see, is Neo here? Neo? Okay, what about Darren Ayrton? Okay, yeah, so any guess about what the sample covariance is? If I want to look at, it's kind of like halfway between this and this, sample covariance, where I'm looking at the interaction between x, j, and y. Any guess how I'd write that? Okay, so it's basically going to be, so in this case, you can see I'm squaring this term. Here I'm squaring this term. What if I took one of these and put them inside the average? That's what we're going to do. So we got I equals 1 to n of yi minus y bar times xij minus x bar j. And this is called the sample covariance. Co because you're looking at the interaction between these two terms. Okay, and this is the key for prediction because essentially we're trying to use x to predict y. And it turns out that if the covariance is 0, our linear predictor fails completely. Our linear predictor is exploiting exactly this covariance to do its job. Okay, so these are, and this is the notation. As you can see, it's S sub x j comma y. Yeah. Okay, any questions so far? All right, so we have a few more definitions. We have to basically look at the matrix version of these, but I will do that on Friday. And remember that the second half of Friday's lecture will be the linear algebra exam. Question? No, it will be on paper, and you can't bring a cheat sheet. You can't bring a calculator. You won't need a calculator. So just bring what's in your head and a pencil, and I'll see you guys on Friday.
I had to step out to use the bathroom really quickly. I just want to make sure you didn't Carter next time.
No, yeah.
Check the name you called.
First name was Zujun Bai.
Oh, no,
Not you?
no.
Okay.
Just a quick notation thing.
Yeah.
When we have like a matrix with like an I, just like a standalone, this would be like I, where we define I as the row vector. This is like I by 1.
So this is a vector, and then this
Okay.
is saying let's take out the ith entry of that vector. Does that make sense? So I have a vector. In this case, it's going to have n terms, but I'm saying what's the ith term?
But we had to transpose it because this was a row vector.
Exactly. So it's like if I have a column and I say what's the ith term?
Yeah, the same
Or
thing.
if I, ith term is the same, right? That was the point. Like
Yeah.
you can do the column or row. If I have a vector, I ask for the ith term. It doesn't matter whether it's a row or column.
Okay.
I can transpose it. Does that answer your question?
Why can't we just leave it without the transpose? Or does it?
It's correct without the transpose, but then the next step is to kind of write this summation. You should always write what we're summing over, so put a little I there. We want to write this as like some kind of vector matrix multiply, but if we didn't have the transpose here, it would be invalid. Because
It's not an inner product?
the dimensions don't work out.
Yeah. Okay.
So when we do this multiplication, we need that this dimension matches this dimension.
Yeah.
And if this is
yeah.
this would be 1 and this is like n. So that's not going to work. So to fix it, we can do this. So now we have n and n, and we're good. This
Yeah,
is going to
okay.
give us a row vector.
So without the transpose, it would be a column vector, and we transpose it into a row vector.
Exactly.
Got it. Yep.
Hello.
You didn't call it Niels, right? You called it Neo for that
Neo,
second?
yeah.
Okay.
I didn't. The last name is Krnogorak or something.
That's
Yeah.
not me, just making sure.
Sure. Hey.
Is there a good time, do you think, to meet with you to talk about, like,
Yeah, I emailed you today. I don't know if you got it. I did.
no,
Yeah.
I haven't checked it. So,
Monday
since this morning.
at 3. Would that work?
Yeah,
You said
sure.
you had time. Okay.
Yeah, sure.
Have a half hour then.
All right, cool, thank you.
Sure.
I'm just curious what happens if I cannot answer the question.
Oh, as long as you're here, I'm just checking for attendance.
All right.
So yeah, it's not about whether you answered it correctly or not. So yeah, it's just a way of checking attendance and keeping you guys a little bit active. So you think maybe you'll call on me, I better pay attention.